Hello and welcome to our talk, Circumventing the Guardians, how the security features in state-of-the-art TLS inspection solutions can be exploited for covert data exfiltration. My name is Morten Marstrander. I'm a senior security consultant working for the Norwegian cybersecurity firm called Mnemonic.
And I'm Matteo Malvika, a principal security researcher at the software company NortonLifeLock. And here is what you can expect from our talk. First, we're going to present the results of our research that we conducted lately. Then we're going to have a brief overview of TLS inspection devices and more specifically on the hello packet. Then we're going to tell you a short story on how we develop the command and control around this new exfiltration method. And we are going to conclude with mitigation and detection and as a cherry on top, live demo. So during the start of 2020, we came up with an idea on how to exfiltrate data through TLS inspection devices by abusing the SNI field as a container for data exfiltration. Our test validates that this was a widespread issue affecting different types of security solution as well as solution from a variety of vendors. We successfully tested our technique against products from F5 networks, Palo Alto networks, and Fortinet, but this could have affected other vendors as well. We had an excellent cooperation with each of these vendors adhering to the responsible disclosure procedure. Palo Alto and F5 published their own security advisory along with workarounds. Fortinet is going to publish it as soon as they have released a fix for that. This joint cooperation resulted in the two following CVEs. The end product of this research of ours is a proof of concept open source project named Sneakit, which stands for Server Name Indication Concatenator. Sneakit is C2 capable of navigating the file system of the compromised host and exfiltrate files through TLS inspection devices sitting in between, even if the C2 domain is blacklisted and configured to be blocked by the device. Sneakit comprises of two separate but interdependent components. A passive agent that should be dropped on the target that is already compromised. And its goal is to connect back to the C2 and execute the provided command by the operator. Also, we have the C2 server, which controls the agent from anywhere on the internet, acting as the threat actor. So we are about to describe each step involved in this process, but first, an introduction on TLS inspection devices is mandatory.
Yeah, so during the handshake process, the SNI is populated by a value provided by the client, and it instructs the server on the right side of this diagram which host name the client is trying to connect to and what certificate the server should present to the client. In this example diagram, we are using a TLS inspection device, either a next generation firewall or a web proxy of some sorts, working as a legal man in the middle, so to speak, in order to inspect the traffic for malicious content, look up the domain being used in a blacklist, and block or allow said traffic based on the result. So in step one, the client begins by sending a client hello. And in step two, the TLS inspection device forwards this to the server. Fair enough. In step three, the server responds with a server hello and a server certificate, which the next generation firewall or web proxy TLS inspection device performs the following. In step four, it compares the SNI with the server certificate subject name, and thereby authenticating the server. And also it validates if the certificate is trusted or not based on its internal trust store. It then, in step 5, performs a filtering decision based on comparing the content of the SNI to a reputation database of domains and URLs. Then the TLS inspection device completes the handshake by signing an emulated version of the certificate presented by the origin server, and it does this with its own internal CA. This CA is trusted by the client, and thereby the TLS inspection device is able to work as a man in the middle. The inspection device then presents this emulated certificate to the client, while also emulating most of the values in the original certificates, like validity, if it's trusted, untrusted, self-signed, etc. Also, in some cases, we saw some devices that not always emulate the certificate. If it is untrusted, then the device, some of the devices will instead send a reset to the client instead of the actual certificate. Yes. So after that, step 6, the handshake is complete, and the application data. Application traffic starts flowing, and the TLS inspection will first then enforce a deny or allow decision based on the reputation lookup in step 5. In addition, as it is now acting as a man in the middle, it can inspect the traffic and data for malicious content and deny or allow this traffic based on its policies configured. So, what can we do with this? Well, based on how these devices work, we figured out a way to abuse the TLS handshake for exfiltration. In some devices, this will even trigger false negatives in the TLS inspection device logs, which we will show you later in our demo. But first, let's have a look at the client hello in a bit more detail. So here we see a simplified version of the TLS handshake with a focus on the server name indication field, or SNI in short. The purpose of the SNI field is to tell the server which domain or site you want to visit so that it can present you with the correct certificate, as I explained earlier. This originally became a necessity when using virtual hosting, where a single web server hosted multiple sites with different server certificates. And it then had to have a way to know what certificate it should present to the clients. So SNI was the solution. Okay, but what if we do something nefarious with SNI? So here we use a wildcard certificate on the web server for star.example.com. But we add .example.com to the SNI, but we also prepend the data we want to exfiltrate and then code it with the base 32. We use base 32 in order to use a character set that is allowed in a domain name. And so far, here we have proved that it was possible to send data in the SNI if the complete domain name matched the server certificate by using a wildcard certificate in this case, and that it also adhered to RFC standards and allowed character sets in a domain name. So we were able to send the data out. Okay, so what's next? After some tinkering, we discovered a common denominator in every solution we tested. As long as the server presents a valid and trusted certificate during the TLS handshake, the TLS inspection device will always present an emulated version of that certificate to the client, signed by the device's built-in CA. This behavior occurs even if the domain used is blacklisted by a reputation database. As you can see, it's in step 6 in this diagram. It happens before the enforcement decision. So in addition, by serving a self-signed certificate from a server or a unvalid, untrusted certificate, the TLS inspection solution either presents the client with an emulated, untrusted self-signed certificate or a simple TCP reset. So this is to highlight the fact that our exfiltration method isn't just another exfiltration method. It also manages to exfiltrate before the traffic is enforced, blocked in the next generation firewall or web proxy solution performing TLS inspection. It also became a critical function of how we would implement a command and control solution, which Matteo will talk about in his tale.
Yes. So at the very inception of our testing, the channel was only working one way, since every tested solution was blocking the returning traffic coming back from the server, and that was obviously not the optimal scenario. We were stuck and in need for a new way of letting the control server data pass back through the security solution. To overcome this hurdle, we built an interim out-of-band C2 based on the Instagram social network, which employed embedded C2 command and control inside Instagram's own command section. This was enough to get a working demo, which proved our theory to be correct, functional, and hopefully extensible. We were able to remotely control the compromised host and selectively exfiltrate data. Then our next goal was to replace the Instagram component, since it was not stealthy, and we wanted to avoid relying on a third party beyond our own control. In addition, we also wanted to create a synchronous C2. So we continue pursuing an in-band alternative of establishing an end-to-end communication between the agent and the command and control server. On a very primitive communication channel, a basic response will only require a binary yes and no capability. And so we added at that point. A valid trusted certificate gives us a yes, and an untrusted self-signed certificate gives us a no. So we implemented this logic into our sneakcat tool. Let's have a talk about how we can explain a little bit more the mechanism between the agent and the C2. So the agent is shipped with the predefined set of commands, and it starts by looping through every command. And after each loop, it sends a request to the C2, and the C2 replies with an untrusted certificate until a matching command is found. The matching command is obviously the command issued by the C2 operator in this case. Then, when the C2 is matching the command, it replies with a trusted certificate, indicating to the client that it should execute this very command. For example, if the operator has issued an ls command, the agent encodes the file list with base 32 and appends a special training code by the end of it, just to notify the C2 that the payload is over, and then it can just decode everything at once. At this point now, both the C2 and the agent have identical copies of the file list, so the C2 can actually react upon this logic. Yes, if we dig a little bit deeper and deeper, let's see on the agent, from the agent point of view, an example of no matching command and a bad cert from the client side. We can see that the operator, well, the agent in this case, is trying to send a CD command, and we can also see a random string appended to the command. What's that? This is made in order to prevent TLS inspection device from caching the certificate response from our C2. And we can also see that the handshakes failed, so this was not the intended command by the C2 operator. We can also notice that this is not a trusted certificate, since it's Ubuntu generic self-signed certificate. Yeah, and this traffic capture, on the other hand, we can see that the C2 operator, it's actually issued the where command. This is still capture from the agent perspective, and we can see that the handshake has completed successfully. because there's no reset. And we can also see the payload coming through. And on this slide, we can also see that the certificate. It's a wildcard certificate trusted by TLS inspection device because it's assigned by a public, well-known CA. Yeah, and we can also have a brief look at the core functionality on the code base. This is an excerpt from the GitHub repo, and it highlights a few core functionalities of the Sneaker tool. On the left side, we can see the C2 bit where it parses the TLS packet, and in particular the hello packet, and it's just react based on the value inside it with the good context or bad TLS context. So basically, trusted cert and the untrusted cert, as we saw earlier. On the right side instead, we can see the agent code snippet where it actually encodes the common output payload in the base 32 encode fashion. And the payload is actually divided into chunks of the maximum length allowed, and then it's trailed with the finito code, which is a way to tell the C2 that the payload is finished and completed. So you can just parse it to the operator. Yes, then at this point, we decided to build mitigation and detections of our own tool. So first, from a TLS inspection device point of view, we recommend changing the blocked URL categories logic to match the SNI field and thus block or allow any session in case of a match occurring. This should actually be performed before completing the server-side TLS and shake. And this way, the data in the malicious SNI will not be passed to the C2 if the site is already restricted by the blacklist or if it's not matching an explicit whitelist. And we also have detection in the security parameter in the sense that performing heuristic on the client hello SNI. What we did, we have successfully used custom logic to perform an entropy check on the SNI field and detect anomalous SNI by utilizing this method. Mnemonic also developed the Surica IDS signature to specifically detect our tool. Yeah, and finally, we also developed a very early stage proof of concept of a passive SNI detection tool, which is conceptually similar to the well-known passive DNS application. And it works by constantly monitoring and logging every TLS hello packet sent through any network socket interface on the hand host. These generated logs can also be gathered and analyzed through a CM solution against any well-known signature or behavioral analytics. Yeah, let's jump to conclusion.
Yeah.
So core features of today's security perimeter solution is to detect and prevent malicious traffic from passing through. We attack those features from different angles and discover that no TLS inspection solution analyzed the very start of a session. We hope to improve such appliance by raising the bar on how TLS session is handled and scrutinized by these products. We could also speculate that other vendors than those mentioned in this talk are affected by Sneakit, even though it will have been interesting to test every network security solution on the market. We had actually limited resource and scope this time. And we therefore advise vendor to test if their products is vulnerable or not to Sneakit. Again, there's no silver bullet, and defense in depth is it's still chief on that. So it can be taken for granted, but it's still important. And we demonstrated this fact when bypassing the security features of TLS inspection devices. And in addition, end user and enterprises may find it helpful to test their solution with our proof of concept code that it's available on GitHub. So feel free to test Sneakit on your own.
Yeah. So Sneakat is a project conducted by us while we were working in Mnemonic, a Norwegian cybersecurity company. And as we said earlier, it is open source, so feel free to try it out. We have the GitHub link here, and also if you want to read more about the story of how Sneakat came to be, there's a blog post at Mnemonic's website as well. So yeah, with that being said, I think it's time to introduce you guys for a demo.
Yay!
So, okay, let's talk a bit about the demo environment before we begin. It is a simulated environment where we have a simulated compromised client on the inside network. And we have a C2 server on the outside network simulating a threat actor on the internet. And in between the two hosts, we have a Palo Alto next generation firewall using TLS inspection and threat prevention features. So let's go over to the demo. So here, this is the client, and as you can see, I have tried to visit a website here with my browser, and this is the domain name of our C2 server, and I added this domain name to a custom category on the Palo Alto that should be blocked. And as you can see, this is the web page that is returned to me by the Palo Alto device, saying that the traffic was blocked. And yes, it actually is blocked. So
are we safe then?
Well, let's see. Let's try with Sneakat instead of ordinary browsing. So, okay, let's try to fire up Sneakat on the client in the context of the current logged on user. Okay, it's idle, waiting for the C2. Okay, then, so let's move over to the host, our C2 server, and fire up the C2 here. We run it as root because we listen on port 443. So this is the C2. And as you can see, we have a help command here where we can display all our predefined commands. Feel free to extend with more commands. It's open source, so yeah, be our guest. It's basically, most of these are basically aliases of Linux commands that are necessary to navigate in a file system. So now that the client is constantly polling the server, let's try to use the where command to see where in the directory we exist on the client, which is basically the same as the Linux pwd command.
Yeah.
So here we go. We got a reply, the home folder of this user, and it changed our output on the shell as well. So we can see where we are at all times. Okay, let's try something more interesting, see what files are in that directory. So let's try the ls command. Yeah. Okay, that was fast reply. ls command. Okay, so we got a list of 3 files in the directory in the client, and they are indexed with numbers in order to easily identify them when we want to exfiltrate.
Yeah. File number 1 looks very juicy.
Yeah, let's try that. File number 1, exfiltrate. Here we go. Secrets.txt exfiltrated successfully. Yeah, let's have a look at it then.
Wow.
Hey, juicy credentials and yeah.
Yeah, very interesting.
Yeah.
Loot and root.
Yes. So then the interesting question is, what happened in the TLS inspection device? Well, let's have a look, because this was supposed to be blocked, right? So this is the Palo Alto interface. I'm going to open the logs now, refresh them. And here you can see all our SNI registered as URLs in the custom category block. But these things looks like they're blocked, but in reality they were not, as you could see. So these are false negatives, in the log. which is quite interesting. So an administrator would think these were blocked, but in reality they are not. So yeah, that concludes our demo.
Yeah.
Thank you.
Thank you.
If you have any questions, please
Reach out.
reach out.
We're here.
Thank you.
Thank you.